In the previous video, we looked at the different bases and converting between them. So we'll just start the second half of the chapter by just revisiting that briefly to remind ourselves the conversion between them. It's a reminder that when it comes to converting from binary to hex and then obviously to denary ultimately, you need to essentially split the binary into chunks of 4 bits, starting from the right, working your way to the left and padding with zeros if you need to when you come to the end, and then taking each of those parts and adding weighting from 1 to 8 above them for each of the 4 bits, converting that into hexadecimal. Obviously when you get to 9 you go to 10, which is A, B, C, D, E, F, and then when you come to work out the denary, then of course you can use the binary and just put the numbers as above all the way across, making sure you keep the right order. So if you've got 6, 3 in hex, then obviously you keep the representation of 6 on this side and the 3 on this side, and then just number it across the top. So there's some extra ones there just to have a look at in terms of how they're split across. So of course binary is a shorthand, hexadecimal is a shorthand for binary, and of course when you go from binary you can go straight to decimal and in between. Now obviously binary characters, patterns of zeros and ones, are also used to represent symbols and text. Now ASCII, which is the American Standard Code for Information Interchange, initially started with 7 bits. 8 bits for extended ASCII, which was enough for A, B, C, full stop, spaces, and the characters that we'd use in the English language. But of course that was a little bit, I guess, narrow-minded in terms of other languages being able to use computers effectively and the range of characters that would be needed. So obviously quickly it was seen that 7 or 8 bits weren't enough, and Unicode, an international standard, was developed which goes up to 32 bits. So 2 to the 32 is of course a very large number, and if you look on Wikipedia, which we'll have a look at now, you can see the versions of Unicode and when certain aspects came in. So 1998 the euro sign, which will have its own pattern of zeros and ones which relate to a decimal number. We scroll through a bit, you can see other languages are starting to get their representations. Even Egyptian hieroglyphics here in 2009 were encoded in binary, so that you would be able to see that Egyptian hieroglyphic would be understood once it's transmitted around the world by computer to computer. Turkish lira, and probably more famously is the encoding of sort of emojis more recently. And you can see some perhaps languages not particularly known to you. So there's lots of combinations available with 32 bits, and if you type in 2 to the power of 32 into Google, you'll see what that figure is. It's a large number of different symbols or characters that can be represented. So this diagram is supposed to just to represent the fact that ASCII, the original ASCII, is part of Unicode. It uses 8 bits, but then expanded patterns represent all the other characters that we'll be familiar or unfamiliar with depending on your language. Okay, so moving on to images. The 2 main types you need to know for at GCSE for this spec are vector and bitmap. And you really just need to understand that vector stores things as lines, shapes. It uses mathematics to store that shape. So for example, that representation of that image can be stored, and it's got infinite scalability, going small or to large. So the same file size could be sent to somebody up in Bristol on Cameron balloons just to print an image on the side of a hot air balloon. Equally, you could send that to somebody else who makes t-shirts to print that image onto a t-shirt if it's vector based. The same file size, because it's not made up of the individual squares or pixels, and it's defined by some numbers and maths, and it's just scalable depending on what's needed. So file size remains the same regardless of actual size. So that is of course an advantage. But of course disadvantage is you can't represent real life images. You can do some amazing vector art. If you Google vector art, you'll see some great graphics, but they're not real life images. So if you look at bitmap, then that's the technique where you can capture real life and capture an image and store it and break it into small parts called picture elements or pixels. So each square is a certain color, and to abstract, that gives us the image that we see. But if we go into the detail of each pixel, we'll find that's made up of 3 distinct parts: red, green and blue, each having its allocation of bits to it. So let's delve a little bit deeper into that. So if you only have 2 colors, black or white, then we might shade this one black, this one black. We might just make a little sort of cross with this really small version of the problem. Now remember, what we're doing here of course is computational thinking. It's reducing the problem to a smaller version of itself to help understand what we're trying to get at. So if we've got a 1 represents a black and a 0 a white, that's all we can do. We can't have any other colors or grays or blues. If we did, we'd need extra bits. So this would form something like a 1, a 0, a 1, a 0, a 1, a 0, a 1, a 0, a 1. So that's what the file might look like if we examined it. And of course, we examined a vector image, maybe for a square. We'd see something like this, perhaps x and y, as in lines, thickness of lines, color, or in any fill. So as you can see, less data, but I guess the precision and the actual look of the image can't be real life, which is one of the key issues. So bitmap is breaking an image or storing an image as lots of separate pixel elements. Most screens obviously are in the thousands in terms of full HD or getting into 4K. You've got somewhere in the region of over 1,000 by over 2,000 pixels that make up the image. And of course, if you're playing a video game, that might be changing 24 or 60 times a second. And forgetting about compression for now, a pixel, as you can see, each of these 3 together are the red, green and blue elements. It's worth noting that humans see more green due to our evolution. Now looking back at an example of a bitmap image, we can see we've got like a character represented here on a grid of 6 by 6. Now we need to store all of those pixels, and let's imagine we've only got 1 bit per pixel because it's only black and white. Then that's 36 bits. If we divide that by 8, then we'll get it in bytes just to get the number a bit smaller and a bit more manageable. So that's 4.5 bytes. And we can see the file would just be a series of zeros and ones. We might need some metadata to tell us the width of the image and the height of the image, so we can represent it again, reconstitute it back up. So metadata is obviously part of images, and obviously some metadata is vitally important. Otherwise we'd just have a continuous line of white and black. We wouldn't get the representation we wanted. So it is important that we know the dimensions of the image. Obviously we don't need to know the location or the camera that took the image or any of that necessarily, but we certainly do need to know the dimensions. So as you can see here, bit depth is something you need to know about, which is for each pixel element, what does the number of bits mean? Well, 1 bit, if we looked at, is just 2 colors. 2 bits is 4. We've seen this pattern before. 3 The Game Boy original gives us 8 possibilities for each pixel, and so on. Then we get to 8-bit. So you got NES, 8-bit sort of graphics, and then moving on up to sort of 32-bit, which gives us a huge number of bits. Usually only 24 bits are used, so we get 16.7 million different colors. So that's made up of 8 bits for red, 8 for green, and 8 for blue. So if you notice when you hover over anything in Photoshop or GIMP free editor, you'll see that you've got white is all the Fs, which is 255, 255, 255, and then black is 000, and so on. Then every other color in between will be some variant on that in order to get the different colors. So if we look at this one here, for example, this is just 3 of the 6 hex characters. So this represents half of the white. If we look at each F, well, F is 15, and so thus it's a 1, 1, 1, 1. And if you're wondering why 255 for red, 255 for green, and 255 for blue, well, that's because you've got 8 bits. So of course 2 to the 8 will get you 256 different combinations, and the highest value you can have is 255. Okay, so have a look that up for more information. So of course a bitmap, each pixel is going to look something like this. It's made up, as we saw, it's red, green and blue, and the red is split into 8 bits, and a different pattern for each of the red, green and blue gives you different shades or hues of the color, and thus when those are put together can give us the pixel color that we desire from the range of 16.7 billion colors. Now, just looking at sort of transfer of data, if we've got an image such as that's got sort of 2 million pixels, a large high definition image, then obviously we need to divide that by 1024, do a bit of maths to work out what that is in kilobytes. We can divide it down again to get megabytes, and work out somewhere that that sort of image is going to be 1.92 megabytes in size. Remember, it's a big B for byte, little b for bits. So if we're streaming video that's not compressed in any way, just the raw image, let's say, with that sort of resolution, was just storing 8 bits. Now obviously remember from previously, we're going to be storing 24 bits per pixel if it was true color, as it were, as in the full range of possibilities. So this is a reduced version for 8 bits. And that would work out somewhere at 24 frames per second, as in 24 images per second, somewhere around 45 megabytes. So that's quite a bit of data, and that's obviously a relatively small example. So you can see what the need for compression, even at this rate, when your internet speed, your broadband at home can be often, on average, about sort of 30 megabits a second, which is of course divide that by 8, and that's just a couple of megabytes a second. So you can see why compression is needed even with this example. Now sound is the next aspect you need to know about. Now sound is obviously a continuous wave, it's analog, you need to convert it to digital, so you need to take regular samples. Now usually the average is about 44,000 samples a second. So just to explain how that works is you'll need to take like a recording of the amplitude of the wave at a moment in time. Now the more frequently you take that sample and do it at least as much as what Nyquist described, again Google Nyquist to find out some more information, then the more times you sample it, the better the representation of the wave. If you leave it a large period of time, then of course the wave is forever changing, so you won't get an accurate sample. And of course the amplitude If you only had a few bits to store the amplitude, then you're going to be very roughly describing the amplitude, the height of that wave. So the more bits gives you more precision to describe where that wave is at that moment in time. So frequently sampling, lots of bits to store the amplitude, gives you a very good representation of the wave. So if we look at this example here, then the lines represent the sampling, so we sample that wave very frequently so that we're storing a more accurate representation. So the more we sample, the better. So for example, we had 12 bits per sample, 60 samples per second. That's 720 bits divided by 8. That gives us 90 bytes per second. So in 1 minute, that equates to 5.27 megabytes per minute. And again, that's no compression. So again, you can see why we need to compress with the internet speeds and such that we do have. It does make a big difference. And so let's finally get on to the final section, which is how we can reduce the file size. Of course, for transmission over the internet, saves storage space, makes searching for files quicker and easier because they're smaller in content. Now, lossy, of course, as it sort of hints at, is you lose data permanently. So techniques have been developed where you can get rid of the data. It does affect the quality. Some of the times it doesn't really affect the quality so that it's noticeable. It does depend in regard to the screen you've got or the speakers you're listening to, etc. So there are other factors at play. But for sound, obviously, generally MP3, video MPEG-4, image JPEG, there are other compressions available. And for lossless, this is mainly done on text, but it can be done on images as well. And it's looking for patterns in the data using things called run length encoding, which we'll talk about in a second. So when you zip a file, or you go to Google Drive and you download folders, Google will zip the file and download it, and that is usually significantly smaller, and then you can unpack it and uncompress it with Windows, Mac, or whatever operating system you're using, and then you'll get the exact files as they were without any loss, but you've in between reduced the amount of data you've had to send. So first of all, lossy. Now, Netflix a few years ago improved their video compression. Reason for that, of course, is they have to pay other companies that run the internet, run the hardware, switches, the wires, the undersea cables, and of course, if they can send less data across the networks, they're having to pay less for that. So there are many advantages in having an algorithm that it still looks very good, but reduces the amount of data. So these are always being worked on. So MP4 was developed in order to remove the sounds that humans can't hear, and also remove the quieter notes. And obviously MP3 can reduce the CD quality by quite a large factor, perhaps by 10. So that's a massive saving. Lossless, again, you're looking for patterns in the data rather than storing all the data itself. So two techniques to talk about initially is run length encoding, which works well with images and sound data, where you're looking for patterns in the data. So a run of blue pixels, there might be 30, 40 pixels that are all pretty much the same blue. To store that as a certain blue, rather than storing each one of them and storing how many of them there are, for example. Dictionary compression. This is quite a neat way of doing it. Works better for larger files. So we've got the phrase no pain, no gain. So in normal sort of storage, we've got 15 bytes plus spaces, of course. We've got one for each character. And we can create a dictionary that gets sent alongside the encoded compressed version that can reconstitute it back to its original size. So again, it's looking for patterns and storing those patterns rather than the actual data. So no pain, no gain, if we had such a dictionary as shown here, would then look like this binary pattern here. which, because it's stored as a binary pattern, is just 12 bits. So that's quite a savings. But, and the but is, of course, we've got to store the dictionary and do a bit of work the other end. So it really does work on larger files. And the final section for this chapter is about file types. And here are some of the key and the main file types you need to be aware of. General points. Most files are dot something, usually 3 or 4 characters. You can create your own file extension types. If you're writing something in Python, you can store and play around with that. And obviously there are lots of things on the web to show you how to do that. But these are some of the main ones you need to know. And that is essentially the first chapter in the CIE GCSE Computer Science to do with data representation.